Welcome everyone. I am Carl Joseph Samuel from the Department of Biotechnology in Kamaraj College of Engineering and Technology. In this video, we are going to see about the bioreactor and its ancillaries. Bioreactor is a vessel that is used to cultivate the microorganisms for the production of biomass, metabolites or biotransformation products which are the result of an enzymatic reaction. The bioreactor provides a suitable condition such as pH, temperature and other nutrients for the growth of a microorganism or the required condition for the enzymatic reaction. The design and mode of operation of the bioreactor will depend upon the type of organism we are using for the production, optimal condition that is used for the production and the product value and the scale of production. For an optimal design of a bioreactor, we need to know about the physical and the physiological characteristics of the organisms that we are using for the cultivation. Before designing the bioreactor, we need to optimize the certain parameters such as agitation, aeration, temperature, pH, nutrition feeding rate and acid or base values that are fed into the reactor. So, one of the main key differences between a chemical reactor and a bioreactor is the selectivity and the rate of the reaction. In biological process, the products which are required are only produced and all other side products or other byproducts are limited in the production. So, hence it is more challenging than the traditional chemical bioreactors. The fundamental engineering and design principle of a bioreactor should include maintaining the desired biological activity of the organism and eliminating the undesired components that is produced as a result of the product. We also need to consider the capital investment for the process and the product before designing a bioreactor. There are several groups of bioproducts are there. For example, a large volume low value bioproducts such as an alcoholic beverages or bulk biomass producing components or enzymes. For that type of bioreactors, there is no need for sophisticated equipments for the production. For a high value low volume products such as hormones, therapeutics and monoclonal antibodies, there should be a high aseptic environment and the process should be more specific for that type of a bioproduct. So, when we are designing a bioreactor, one concept we should know that is there is no universal bioreactor. A single type of configuration cannot be used for all type of processes. So, each process requires a unique and unique optimal bioprocess equipments and unique optimal bioreactor designs. Sizes of the bioreactor vary according to the environment and the purpose of the biological process. For example, small microbial cells can be cultivated in vessels that are few millimeter cube volumes. Again, in a shake flask cultures, that is we are using in a laboratory scales, shake flask culture is used where 100 to 1000 milliliters are used for production. Laboratory scale fermenters are again that is also used for 1 to 50 liters in the volume. Pilot scale fermenters will be of 0.3 to 10 meter cube and in a plant scales 2 to 500 meter cube fermenters are used. The number of parameters that are monitored inside a bioreactor is limited by the number of sensors that can be installed in the bioreactor, which we will be seeing in the future next slides. So, for a typical fermentation process, the fermentation process starts with isolating a desired organism. Once we isolate the desired organism, we will optimize the parameters for the growth of the organism and we will have an inoculum stock culture. So, that stock culture is then transferred to a shake flask fermenter. This shake flask fermenter will have around 1 liter or 1 or 2 liters of volume of inoculum. So, this inoculum is then transferred to a seed fermenter which will be around 10 to 50 liters. Biomass that is produced in the seed fermenter is then used as an inoculum for the production fermenter. From that production fermenter, culture fluid is collected and then used for the separation and purification of the bioproducts. This is a typical bioreactor that is used in the laboratories and in the production systems. So, bioreactor vessel, it consists of various ports for allowing the various inlet and outlet like acid, base, inoculum. So, that will be placed in the top and bottom of the bioreactor. At the bottom of the bioreactor, there is an outlet valve is also included. So, the jacket is included for maintaining the temperature inside the bioreactor and other components are there. The components of the bioreactor is explained in the next slides. So a typical bioreactor vessel, it consists of a vessel. The vessel is either made up of a stainless steel or a glass. So the fermenter, it is a large cylinder that is closed at the top and the bottom, which can be connected with various pipes and valves for the bioprocess. The vessel is designed in such a way as to work in a controlled environment. So like I said earlier, glass and stainless steel are the two common materials that is used for the production of bioreactor vessels. Glass bioreactor vessels are used in the laboratory scale or small scale productions, while stainless steel bioreactor vessel is used in the industry scale bioreactors. Generally, the stainless steel consists of 4% or more chromium. So, for bioreactor vessels, stainless steel consists of more than 10 to 20% chromium. Again, also nickel is also added to improve the strength of the stainless steel for the bioreactor systems. Next, we are going to see about the heating and cooling system of a bioreactor. Temperature is an important part in the growth of a microorganism. If a temperature varies inside a bioreactor, the enzymatic activity inside the cell can be altered. The cell has a maximum activity at an optimum temperature. So, it is important that an optimum temperature is maintained throughout the process. For the maintenance of optimum temperature, there are various heating and cooling systems are implemented in the bioreactor. Heat is generated in two ways inside the bioreactor process. One is through the biochemical reactions and another is through the mechanical agitation that is provided. So, the heating and cooling system involved in the bioreactor is a cooling bath, that is a thermostatically controlled cooling bath or a heating bath, and again or with a thermostatically controlled internal coils. So, that will provide a heat, and while the cooling system, the cooling jackets provide the cooling system. It is important to note that the cooling system is required during the sterilization process to cool down the contents of the bioreactor. The next important system is the aeration system. The aeration system is provided by two components inside the bioreactor. One is through sparger and another one is through the impellers. Sparger is required for the transport of air into the bioreactor system. Oxygen is provided through the air that is transferred through the sparger inside the bioreactor system. So, the air that is transferred inside the bioreactor system is then equally dispersed by using the impellers. The steering by the impeller is important for two things. First, it is used to mix the gas bubbles through the liquid culture medium, and it is also used to mix the microbial cells for the equal distribution of the solid materials that is present inside the bioreactor system. These are some of the most commonly used sparges in the bioreactor system: porous plate, perforated plate, single orifice nozzle, multiple orifice nozzle, perforated rings, spider type sparger, injector type sparger, and bubble cap. So, these sparger systems allow the air into the bioreactor system through small bubbles. These bubbles are then equally distributed through the use of impellers. Impellers are important for the mixing of the contents of the bioreactor. Inside the bioreactor, the nutrient media is present to provide the nutrition for the microbial cells, and there is an oxygen that is and the air bubbles are present to provide the aeration for the microbial cells. So, these two components need to be mixed thoroughly to provide a uniform mixing inside the bioreactor. So, impellers ensure uniform distribution of nutrients, cells, and other components to prevent the gradient from forming inside the bioreactor. It also facilitates the dispersal of the oxygen bubbles by breaking down the oxygen bubbles into smaller bubbles, thus increasing the surface area for the oxygen mass transfer. It also prevents the localized heating or localized cooling inside the bioreactor by mixing the components of the reactor uniformly. Impellers are also important to avoid the settling of cells, nutrients, or other components that is present inside the bioreactor system. These are some of the most common types of impellers. So, these impellers provide various types of flow: radial flow and axial flow. So, for example, the axial flow, the liquid is moved in the direction of the axis of the impeller shaft. In radial flow, the liquid is mixed in the direction perpendicular to the axis of the impeller. The liquid is mixed along with the tangent of the bioreactor. So helical type of impellers allow the axial flow. Propeller and turbine are the two most commonly used types of impellers for a bioreactor system. Another important thing for the bioreactors is baffles. Baffles are used to prevent the vortexing inside the bioreactor. When a constant agitation is provided, there is a chance of vortex forming. So that vortex will prevent the uniform mixing of the components that is present inside the bioreactor system. To prevent that, baffles are used. So baffles are present inside the bioreactor system. These are generally small metal strips that is perpendicular to that of the surface of the bioreactor vessel. So it is usually 1/10 of the vessel diameter. So it is used to improve the aeration efficiency. The wider the baffles, the agitation effect is improved, while the narrower baffles, the agitation effect is reduced. So baffles are attached to the cooling coils generally to increase the cooling capacity of the fermenter. Feed ports allow the controlled flow of nutrients, gases, antifoam agents, inoculum, acid or bases for during the fermentation. There are dedicated ports for the use of each components that is allowed inside the fermentation system. Valves will regulate the flow of the inputs, and it will allow us to maintain the sterile environment inside the bioreactor. So there are several type of valves are there. Inlet valves for the nutrient and air addition. There are outlet valves which are used for sampling during the process, harvesting of the completed biomass or waste removal. There are pressure relief valves that is used for the to prevent the over pressurization during the sterilization or during the fermentation process. There are drain valves that is used to empty the bioreactor system. These valves are generally made in stainless steel or using other autoclavable materials. There are other monitoring systems that are also present in the fermentation systems. So there are pH sensor that is used to monitor the pH inside the bioreactor system, and this will feed the data into the control system, which activates the acid pump or an alkali pump as required based upon the set initial values. DO probes will monitor the dissolved oxygen content during the fermentation process. Temperature sensor regulates temperature sensors monitor the temperature and allows the control system to regulate the temperature by switching on or off the cooling system or the heating coils. Pressure sensor are used to monitor the pressures that is building inside the system and to regulate the pressure that is present in the system. Foam detectors detect the presence of foam inside the system and activates the anti-foaming dispersal systems. Optical density sensors are used to monitor the cell density or other components. Optical density sensor are used to monitor the cell density or other components that are measurable by the optimal control system. The various monitoring and control system that is used in the fermentation will be discussed detailed in the next video. Thank you for listening. Thank you.